Hello, and welcome back to Scientific Terminology. Today we're going to be talking about constants, which are nature's special numbers. These are values and numbers that are found naturally in equations and other such things that make them very special. So let's take a look and see what exactly these constants are. So like I said, a constant or a physical constant is a physical quantity that is believed to be constant value in time. They don't change. It's always happened. It's a natural value for whatever the purpose is. This is different from a mathematical constant, which has a fixed numerical value, but no direct involvement with physical measurements. So in math, there are these special constants that just kind of show up in mathematics, whereas these physical constants are specifically tied to something in nature, some measurement you can make. So let's talk about the physical constants first, and we'll go through each one of them individually. The first one is the gravitational constant, which is always big G. The gravitational constant G is the constant used to calculate the pull of gravitational forces on objects. It is used in Newton's equation for gravity and Einstein's relativity equations. This here is the Newton gravity equation, and you can see the big G is in here with the masses of the two objects and the distance they are away from each other. So this number needs to be in there, otherwise the math just doesn't work out. It's a natural constant that does not change. The speed of light, or little c, is the speed that light travels in a vacuum. It is 3 times 10 to the 8 meters per second, and the speed of light is the universal speed limit for all matter in the universe. It takes light 8 minutes and 17 seconds to reach Earth from the sun because, right, if it's traveling that fast, that's how long it takes for light to get from here to here, which is a really long way. The next constant is Planck's constant, which is little h. Planck's constant is important in the measurement of a photon's energy level. The constant times the photon's frequency is the energy of the photon. So this is a really important physical constant that is used to measure energy in light. Planck's constant was derived from observing black body radiation and its data, like seen above. So using these graphs, we were able to determine what Planck's constant was. Or, well, I wasn't able to. Planck was. The next ones are called the Yugawa Couplings, and there's 9 of them. Yukawa Coupling is a part of particle physics and is related to how different fields interact with each other. It deals with the way that the strong force interacts with hadrons, as well as the interaction between the Higgs field and quark and lepton fields. That's about as far as I can explain it. I'm not a particle physicist. I don't 100% understand everything that goes on in there, but I do know that this is important, especially when we're dealing with particle physics. That's one of the major spots that science is working on today, so it must be a pretty big deal. Another constant is the Higgs field potential parameter, another part of particle physics. The Higgs boson particle is a fundamental particle that decays rapidly, but it also explains why some particles have mass. So these potential parameters are important in understanding why things have mass and why some things don't. Another one is the quark mixing matrix parameters, another part of particle physics. The quark mixing matrix describes the flavor and the changing weak interactions of these fundamental particles. The matrix has been changed and added to several times, and it specifically describes the quantum states of quarks when they're propagating freely. Quarks are a fundamental particle that are smaller than our protons, neutrons, and electrons. Didn't know those existed, huh? Well, they do. And I believe this is the last one. The 3 coupling constants for gauge groups is a part of general relativity and elementary particle theory. Gauge groups help explain the field theories of elementary particles, and they're also used right in general relativity. So they're also rather important. These are the kind of things that our physicists are trying to figure out, the big questions of the day. Oh, there was one more. The QCD vacuum phase is another essential part of particle physics, and it relates to gauge theory and deals with the flavoring of quarks. So it's all part of that fundamental questions about elementary particles. Let's move on to mathematical constants. We mentioned those at the beginning of the video, and these are ones that are not tied specifically to physical phenomena, but, deserve their couple minutes of fame here. So let's talk about our mathematical constants. The first one is pi, and pi is the ratio between the circumference and diameter of a circle. It's an irrational number and is the subject of a world record for who can memorize the most digits. The circumference of a circle with a diameter of 1 is pi. So if you have a circle that has a circumference, or with a diameter of 1, its circumference will be 3.14, blah, blah, blah. So pi is an important, naturally occurring number that shows up in math all the time. An imaginary unit, or I, is a mathematical concept which extends the real number system. Imaginary numbers are created by squaring negative numbers. So when you're learning about square roots, you learn that you can't square a negative number because it doesn't work. Well, mathematicians said, well, what if they did work? I is what allows that to happen. I is the square root of -1. Euler's number, or E, is something you might have seen in a higher level math class. Euler's number is the exponential growth constant, and it was discovered by calculating compound interest, thanks to Jacob Bernoulli. Exponential growth is represented by the green line, and that's where growth starts growing slowly, but then starts increasing rapidly until it almost approaches a straight vertical line. Pythagoras' constant was important due to his Pythagorean theorem, and it's the square root of 2, and it is the length of a hypotenuse when the sides of triangle measure 1. And this happens no matter what. It's a mathematical constant. Pythagoras' constant is the square root of 3, and that is the measurement of the height of an equilateral triangle with the side lengths of 2. So once again, kind of following Pythagorean's theorem here, the square root of 3 is always going to be the height of this triangle if this equilateral triangle has 2 as the length of the sides. The Feinbaum constant, or alpha, is used in logistic maps. It's a map of polynomial behavior and is an example of how chaotic behavior can arise from simple nonlinear functions. Unfortunately, there's not much more I can say about that because I do not know high-level mathematical analysis, but I do know that if it's a constant and they've given it a special Greek letter, it's probably pretty important. Avery's constant is an irrational number that arises from a special series. It arises naturally in several different physical problems, and as you can see, this is where you can derive it from, this equation here, where we have a series adding on increasingly smaller fractions. The golden ratio appears often in geometry, and it's the length of a pentagon's diagonal. The length of a pentagon's diagonal is that Greek letter times its side. That one escapes me all the time. I don't remember what this one is called, but it is a Greek letter, and it is derived from these pentagons. The Euler-Maceroni constant is the constant which appears in Merton's third theorem and has a relation to the gamma function and the zeta function. Not 100% sure what that means. There's a pretty graph of it right here. Very exciting. Conway's constant, which is called lambda. Conway's constant is the invariant growth rate of all derived strings in a look and say sequence, and its value is 1.30357. This here is a look and say sequence. Khinchin's constant, capital K, is a real number r as written in a simple continued fraction shown on the right. K is approximately 2.6854520010. So as you can see, this fraction gets bigger and bigger and bigger, or I guess technically smaller and smaller and smaller as it goes on. Yeah, that makes sense. Oh, it does get bigger. Never mind. It gets bigger. It's going to be bigger than 1. The Glacier Kingland constant, A, is a constant defined as the limit seen to the right. It is an important constant that appears in the Riemann zeta function, which plays a pivotal role in analytic number theory, which sounds very important. A is approximately 1.282427191, and as I can say, since it's part of this theory about analytical numbers, probably pretty important. Chaitin's constant, which is omega, is the real number representing the probability that a randomly chosen Turing machine will halt. It is used in computer science, so it's pretty important with all that computer stuff, which is becoming more and more important these days. Who would have thought computers would have worked out? And there you have it. Those are all of the physical and mathematical constants that I could find on the internet. Thanks so much for watching, and please subscribe. Ring the bell and hit the like button so I know that you're watching these videos. And then, of course, comment and tell me what you want to learn about. I will do my best to put that stuff out there so you can learn what you want to learn. Either way, thank you so much for watching, and I'll see you next time.